Welcome to Piano Unlocked, where I'll be sharing with you the keys to playing the piano. Now, the first key to playing the piano is, well, knowing what the keys are. Take a quick look at the keys and you'll notice two things. First, the keys are two colors, black and white. Second, the black keys are grouped in a repeating pattern. There are two black keys in a row, then three black keys, then two black keys, then three, all the way up and down the keyboard. Oh, by the way, on the piano, up is to the right of the keyboard and down is to the left. That's because the notes go up in pitch the further to the right you go, but we'll talk more about what that means a little bit later. The white note to the left of the group of two black keys is called C. No matter what part of the keyboard you're playing, no matter how far to the left or to the right, if there's a white note to the left of the group of two black keys, it's a C. The musical alphabet, in English-speaking countries that is, goes from A to G. That's just 7 letters divided between 52 white keys on the piano. So those letters repeat 7 or 8 times over the course of the keyboard. Aren't you glad you just have to remember 7 different names for the notes instead of 52? The black notes also have names, of course, and they're just as easy to remember, but we'll talk about that another time. If I play any two Cs, they're going to sound very similar together. So similar, in fact, that they kind of blend together. The only difference between them is that one is lower and one is higher. One will be at a pitch that someone with a deep voice might feel comfortable singing, la la la, and one will be at a pitch that someone with a high voice might feel comfortable singing, la la la. But every C will sound, well, it'll sound like a C. If I play a C and some other note, it's not just that one note is lower and one note is higher, it's that the two notes have a different quality from each other. They don't blend together in quite the same way. And the reason for that has to do with the science of sound. So bear with me while I change into my professor clothes so that we can do an experiment together.
Did you know that the colors of the keys on keyboard instruments like the piano were not standardized until the 1800s?
Early keyboards often used ebony where today's white notes are, with plain maple on the raised notes in between where today's black notes are. When ivory became available in Europe, it was used on those raised keys to make more of a contrast with the main body of the keyboard. Mozart's piano, well, it was actually a forte piano, had black keys on the lower level with raised white keys between them. There are several theories about why the colors switched. Ivory was expensive, so maybe wealthy people wanted to show just how much they could afford by using ivory on the majority of the keys instead of as an accent color. Maybe it had to do with how well ivory can withstand the wear and tear that comes with heavy piano playing. And maybe it had to do with some difficulty seeing the dark spaces between close together dark keys. It's easy to see the border between white keys on a modern piano. What we do know is that these days piano keys, mostly made of plastic, could be any color at all. But piano manufacturers have stayed across the board with white keys on the lower level and black keys on the upper.
I'm sorry it took me so long. I couldn't find my lab coat. But fortunately, this experiment is not messy at all. And you'll probably be able to do it along with me because all you need for it is a simple rubber band. Sound is made by objects vibrating. And you are able to hear sound because the air around the objects also vibrates. Your outer ear, the part that you can see, is shaped in a way that draws the vibrating air into the ear canal and to the eardrum, which is called by the scientific name tympanum. Now, what does that word remind you of? That's right, timpani, a kind of drum used in orchestras. It's like you've got a tiny little timpani inside each one of your ears. That's why it's called an ear drum. And that drum vibrates in response to the vibrating air and makes the tiny bones in your middle ear vibrate. The fluid in your inner ear, the cochlear fluid, also vibrates, and so do the minuscule hairs in the cochlea, the stereocilia. The vibrations of the stereocilia turn into electrical signals, and that's what the auditory nerve carries to the brain, which interprets it as sound. So what does that have to do with why any two Cs on a piano or any other musical instrument sound alike? And what does it have to do with rubber bands? Well, vibration is movement, right? But it's not just any kind of movement. See, if I tap my face like I'm trying to figure out how to explain the concept of vibration, you wouldn't call that movement a vibration. It's just a tap. Vibration is steady, rapid, back and forth movement around a central point. It's the kind of movement that happens if I stretch and pluck this rubber band. If you do this at home and look very closely, you can see the band overreact. I'm stretching it out, and when I pluck it, it very rapidly contracts not back to its original position, but to something a little further than that. And then it ricochets back out again, and back in. That kind of ricochet movement is vibration. And when I plucked the rubber band just now, you heard it. Human ears can generally hear when an object vibrates between 20 times per second and 20,000 times per second. Dogs can hear when something vibrates up to 45,000 times per second. That's why a dog will respond to a dog whistle even though the person using it can't hear it. It's not that the dog whistle is too quiet. It's that the rate of vibration, the frequency, is too high. So what determines the frequency of vibration? One answer is tension. If you take a rubber band but don't stretch it very much, when you pluck it, it will move back and forth almost lazily. It'll reach the top and the bottom of its ricochet trajectory much less frequently. That means it has a lower frequency of vibration. But there are two situations that will make a rubber band vibrate at a higher frequency. First, I'm going to pluck the rubber band as I slowly stretch it out. The pitch went higher and higher, didn't it? Right along with the frequency of vibration. That's because the rubber band was under more tension. You can actually feel the resistance of the rubber band against your fingers if you do this. It just doesn't want to stretch any further. And if you pluck it when it's under this amount of tension, it goes nuts, just vibrating faster than it would ever do if it was more or less at rest. Now watch what happens if I don't stretch the rubber band out a lot, but instead shorten it. That's close to the sound that the rubber band made the first time, before I stretched it out all the way. Okay, but now watch this. I'm not going to stretch the rubber band anymore, but I'm going to put my thumb in the middle. This was the sound without my thumb, and now with my thumb. Suddenly, the pitch got not just gradually higher like when I stretch it, but suddenly a lot higher. That's because my thumb acted as a stopper. Instead of letting the entire rubber band vibrate, only the portion past my thumb was free to move. So the band was a lot shorter. All of this was cut off. With less band, it had less distance to travel and was able to get back and forth over the same point more often, with a greater frequency. So length of string also determines the frequency of vibration. But if a shorter string makes a higher sound and a longer string makes a deeper sound, then when I stretched the rubber band out before, shouldn't the pitch have gotten lower and lower instead of higher and higher? Well, no. See, when I stretch the rubber band out, I'm not actually making a longer rubber band, even though it may look like I am. What I'm making is a tenser rubber band, and it's the tension that raises the pitch. But when the tension doesn't change, it's true. A longer string makes a deeper sound, and a shorter string makes a higher sound. And that's what we just saw when I used my thumb to shorten the string. So how about I change out of this suit and we can go back to the piano and see how that really works on a musical instrument. You can see that the lower strings, the strings to the left, the strings with a deeper sound, are longer than the strings on the right, the strings that produce a higher sound. By the way, you might also have noticed that the strings aren't plucked, but are instead hit from below by a kind of felt-covered mallet, or as it's called on the piano, a hammer. If you look really closely toward the bottom left of your screen, you'll be able to see it poking up from underneath the strings. See that? Hitting a string will cause it to vibrate just as well as plucking it, so long as the string is stretched and has the freedom to vibrate. You might be noticing something else too, something that I wasn't able to demonstrate on the rubber band. The deeper, longer strings are also thicker. The greater mass of a thicker string slows down the vibration and therefore produces a lower pitch. Okay, so now we know why some notes are higher than others, and you've gotten a really comprehensive explanation of why the notes go up on the piano keyboard as they go further toward the right. But I haven't said a single word about why two C's sound similar to each other. Well, here's the reason. It's the overtones. The overtones are a band of superheroes saving your ears from thin, pale, uninteresting sounds. Do you enjoy the rich, warm melody of a cello? Thank the overtones. Do your ears perk up at the brilliant call of a trumpet? Thank the overtones. Every time a note of music is sounded, every time a bird sings, every time a train whistles or a car horn beeps, no, really, even then, the overtones run around like crazy to get sound from every part of whatever is making the sound, whether it's a rubber band or your vocal cords, or the floor your upstairs neighbor is walking on in very heavy shoes. The overtones are not actually superheroes, though I personally think they're downright super. But really, they're just something that happens because of physics. See, when a string vibrates, it vibrates both as a whole and in parts. Remember, frequency, which is what determines pitch, is a question of how often a string, or a part of a string, goes back and forth over a central point. Let's imagine that the entire string is vibrating in a way that it crosses its central point, let's say 261.6 times per second. Well, it turns out that each half of the string crosses its central point 523.2 times per second, exactly twice as fast. And each third of the string crosses its central point 3 times as fast as the whole string, and each quarter and each fifth, and so on to infinity. But these vibrations get progressively weaker as you take smaller and smaller portions of the string. Remember, the human ear can hear vibrations with frequencies from about 20 to about 20,000 times per second. So if a string is vibrating at 261.6 times per second, you can hear quite a number of the vibrations that a portion of the string produces as well. These vibrations are the overtones. You can kind of hear them very faintly over the main tone. They're also called partials because they're made by just a part of the entire string. But as I said, those partials are relatively weak in comparison to the vibration of the string as a whole. That vibration is called the fundamental, and that is the primary tone that your brain identifies when you hear a sound. But the whole array of overtones that surround the fundamental is what gives the sound its resonance. Now, I didn't come up with the number 261.6 out of nowhere. That's the frequency of vibration of the middle C on the piano. Now get this, if you divide a C string in half, each half vibrates at 523.2 times per second, and that produces the next C up. If you divide a C string into thirds, that partial is still plenty low enough to hear at 784.9 times per second, but that is not a C. It happens to be a G, and we'll talk about that in another episode. But if you divide the C string into fourths, which is the same thing as dividing each half into halves again, you get another C. Every C vibrates twice as fast as the C before it. Every D vibrates twice as fast as the D before it, and every E. And every note, whatever kind of note it is, vibrates twice as fast as the one before it. Okay, but why do they sound alike? Back to the overtones. Remember that a high C comes from a string that is half the length of its lower neighbor. Well, that means that that lower neighbor comes from a string in which each half vibrates at the rate of a high C. A lower C contains two high Cs in its sound. Again, Vibrations from just a part of the string are comparatively weak, so the lower C is what you identify as hearing. But the higher C is the strongest overtone in that lower C, and that's not their only overlap. If you divide the lower C into fourths, it's like dividing the higher C into halves. If you divide the lower C into sixths, it's like dividing the higher C into thirds. So that higher C is not just already present as the lower C's strongest overtone, all of the higher C's overtones are also present among the lower C's overtones. That's a lot of overlap. And that's also why if I play any two C's together, they sound like they have kind of the same tone quality. But if I play a C in some other note, no matter how nice they sound together, they don't really sound like they belong in the same category. Oh, here's something else that's kind of fun. If I silently press down a C, and then I very loudly play the lowest C on the piano, listen to what happens. Do you hear that? It's kind of like an echo of the higher C, except the only note that I've actually played is the lower C. When I hold down the high C, a piece of felt called a damper that normally rests on the strings is raised up and leaves the string free to vibrate. The overtones in the low C vibrate throughout the piano, and due to a phenomenon called sympathetic vibration, any object, in this case a high C string, any object that vibrates at the same frequency as those overtones will do so. Just one more way in which the high C is literally contained within the low C. That's called consonants. Now, you may have heard that word before in a way that means agreeable or something that fits together with something else. For example, the fact that you're watching this video is consonant with the fact that you're interested in learning the piano. But what consonants literally means is that something makes a sound at the same time that something else makes a sound. They sound with son, kun, each other. Ants is a suffix used to show that something is a fact or a phenomenon. So consonance is the phenomenon of two things inherently making a sound together, like the overtones that occur when you play a low C. But back to finding keys at the piano. Before that little science lesson, that big science lesson, we talked about how to look for a C. It's the white note to the left of the group of two black keys. Well, now that you know all about overtones and vibrational frequencies, you can also use your ear as a backup. If you're playing a C and you're not sure if the other note that you're playing is also a C, and sometimes when you're first starting the piano you might forget that a C is on the left of two black keys and wind up playing the note that is on the left of three black keys, which is not a C. Well, if you're not completely sure that you're playing a C, you can ask yourself whether it sounds essentially the same as the other C, just higher or lower. If it does, that's a good sign that you're playing two Cs. Now, I mentioned that in English-speaking countries, the musical alphabet goes from A to G. So now that you know where C is, you could find all the other white notes on the piano with reference to C. For example, D is just one note away from C, right? Yep, that's right, it sure is. But don't do that. If you do that, you'll wind up having to count up or down 3 or 4 notes from C if you want to find a G, for example. C, D, E, F. Okay, there's G. And sure, sooner or later you would learn all the notes and not have to count out loud each time. But the initial period of counting like that would make for some slow, frustrating, hunt and peck piano playing. And I really believe it would make you a less secure player over the long term. So let's learn a few more notes completely independently. Just like we learned where C is with reference to the groups of black keys, we can learn 3 other notes the same way. E is to the right of the group of 2 black keys. F is to the left of the group of 3 black keys, not to be confused with C, which is on the left of the group of 2. and B is to the right of the group of 3 black keys. So over the next few days, play these 4 notes a whole lot. Not for hours at a time, but here and there throughout the day, take a minute, literally just a minute, and quiz yourself. Make it a game. Don't do the same thing every time. If you find all the C's and then all the E's and then all the F's and then all the B's every single time, that's going to get really boring really quickly. And I don't think you'd learn as much as if you mix it up and make random little challenges for yourself. So maybe you'll go to the piano once and find all the F's. And then maybe the next time you go to the piano, you'll decide that you want to alternate F's and C's to do all the notes that are on the left side of a group of black keys. Or maybe you'll decide to do a lightning round and you'll play all of the E's as fast as you can, except that after every third E, you'll play a C. Sometimes you might go all the way up the keyboard and sometimes all the way down. Or you might even go from the center of the keyboard and move in opposite directions with both hands. Once you've gotten really comfortable finding these 4 notes, C, E, F, and B, it's easy to fill in the other 3. Try not to think of them in reference to those 4 notes, though. D is next to C is accurate, but it's not as effective a way of learning the note as something like D is the white key in the center of the group of 2 black keys. The more independently you learn everything related to the piano, the more confident and the more natural your playing will be over the long term. So now that I've said all that, did I leave any questions unanswered?
Yes! If the musical alphabet goes from A to G, why are you starting with C? And what's the alphabet if you're not in an English-speaking country?
Excellent questions. But after that big discussion about overtones, I don't want to overwhelm everyone with a deep dive into music history. So I'll save that for next time. And did I leave any of your questions unanswered? If so, send me an email at myron@pianounlocked.com, and I will answer them in one of the next episodes. And make sure to subscribe on the website so you never miss a single key. Until next time, happy practicing!